Yes, thank you. And welcome everyone to the last talk in our Quantum Summer series, hosted by the Harvard-Radcliffe Society of Physics. My name is Minchul Park. I am an undergrad studying chemistry, physics, and mathematics at Harvard, and I'm one of the organizers of our Chilloquium speaker series. Today, we are very honored to have Professor Ana Maria Rey from JILA speak with us today. As always, if you have any questions at any time, you can raise your hand in the Zoom participant sidebar and we will call on you, or you can privately send a message to me and I will ask for you. We encourage you to raise your hands to ask questions yourself in person in order to make this feel as conversational as possible. So we'll generally be prioritizing questions asked in person over privately messaged questions. In the spirit of keeping this a more relaxed and personal conversation, we also request that everyone be muted unless they are speaking and also have their video on if you are willing and able. All right, so with that, let's get started. So Professor Ana Maria Rey is a fellow of JILA and a fellow of NIST. Professor Rey worked as a postdoctoral fellow at the Institute of Theoretical Atomic, Molecular, and Optical Physics at Harvard from 2005 and 2008. Her research interests are in the scientific interface between atomic, molecular, and optical physics, condensed matter physics, and quantum information science, specifically on ways of developing new techniques for controlling quantum systems and using them in various applications ranging from quantum simulations to time and frequency snapshots. Professor Maria Rey, please.
Oh, thank you very much for the introduction, and it's a very nice pleasure for me to speak today. Please, I encourage you that if you have questions, just ask during the middle of the talk, just interrupt me. So maybe I will start by first thanking the organizers, Minchul, for the invitation. And well, my hope is to describe today for me, the fascinating idea of how we can use atoms and light to create atomic clocks that is, they're the most precise timekeepers you have ever imagined. So I'm going to walk with you about the inner workings of the clocks. And well, even if I don't convince you become a clockmaker yourself, I hope that at least I can convince you that atomic clocks are not only fascinating, but they're useful and they help us to unravel the mysteries of the universe and to build the next generation of quantum technologies. All right, so I was encouraged to describe a little bit about myself. So I'm here in Boulder, Colorado, and I work at JILA. This is the very nice building inside the CU campus, and at NIST, Boulder. That is about 10 minutes biking distance. During my PhD, I did it at the University of Maryland, College Park, but interesting, I also was part of NIST. So I have been a NIST-related person all my life. And well, instead of telling you all the details of my undergraduate of my PhD here, I'm going to tell you a story that connects all of it. The important part is, I have always been interested in ultracool atoms and light and how can we use them for something useful. So I want to start this talk also by acknowledging my close collaborator at JILA, who is the actual experimental clock maker. This is, you can see Jun Je, and his fantastic group of students and postdocs, and of course of my theory group. All right, so let me start this talk by introducing our protagonists, our main persons or main ingredients of this talk, that is ultracool atomic systems. So ultracool atoms generally are systems that of course are ultracold, but that means that we can relate this temperature to a measure of the kinetic energy. Remember that hot particles, well, they move very fast, whereas cold particles are very slow. So if we used to characterize what we mean by cold, we're using a thermometer that we have a Kelvin scale. We can see that atoms at the room temperature move very fast, almost at the speed of sound, 300 meters per second. So of course, at this temperature is very hard to manipulate these atoms. So if we now think at the coldest temperatures that you can have in the universe, you can think the outer universe, and the temperature is not as different as the temperature at which helium condenses, that is about 4 Kelvin. But if you think about at this temperature, the helium atoms are still moving very fast, 90 meters per second. So one of the big accomplishments that we have done in the last couple years is the capability to actually laser cool and atoms that between 10 to the 4, 10 to the 6 atoms at very cold temperatures between 1 and 1 to 10 microkelvin at the velocity of just a few centimeters per second, and later we are going to tell you that we can go even colder. So but these few steps of cooling the atoms was done by using lasers, and actually the idea is very simple. The idea is that if we have, this led to the Nobel Prize in Physics in 1997, and the main characters were Stephen Chu, Cohen Tanuji, and Bill Phillips, and in particular, Bill was a very important a person who is career. I will show a picture of Bill soon, but I mean, actually he was the person who, when I started my PhD in Maryland, convinced me that ultracool atoms are really fun. So what he did, he used lasers to bombard the atoms, and with that remove kinetic energy and slow them down. So this is a picture of Bill giving one of the talks to the grad students the first week of my PhD. So how does laser cooling work? Well, we have atoms that we illuminate them with light, and we choose a frequency of the light such atoms going in opposite direction are the only ones that are going to absorb the photon. With that, then the atoms absorb photons, and it feels a momentum kick in the opposite direction of which is moving, reducing its speed. And then this is done many times until we can reach colder temperatures. The process, of course, has to be done in all directions, and this happens in what is called Magnetoptic Trap. And with that, we'll be able to cool atoms to of the order of microkelvin temperatures. But this is not enough in order to reach the temperatures that actually we want. And in order to go about 100 nanokelvins, a bit lower, what we do is to treat the atoms as if it were a coffee in a cup. So basically, you can, if you typically process how you cool down the coffee, is because the hottest molecules evaporate out of the coffee, and then the remaining molecules remain cold. And this is what we do with atoms. So these atoms, in order to, instead of having a cup, we trap the atoms, and in many cases we use the fact that these either light or the fact these atoms have a small magnetic moment, and then we can use magnetic fields to trap the atoms. And then what we do is that by changing the depth of the trap, then we can let the atoms escape. So let's see if my animation can work here. I mean, maybe I need not to have the, okay. Yeah. So the idea is that we reduce the depth of the trap, and therefore only the coldest atoms, and as a consequence, then they rethermalize, and we can get a gas that is much colder and at the temperature that where interesting quantum phenomena start to happen. And in particular, one of the interesting consequences was the formation of a Bose-Einstein condensate that was awarded the Nobel Prize in 2001. This is one of the very interesting developments that happened just a few years before I started my PhD. And the interesting part is that when we start to create a BEC, we start to create a window to explore the quantum world. We know that there is the particle-wave duality, so the atoms can behave like atoms or particles or waves. So, but at very hot temperatures, the particles, the atoms are more like billiard balls, that they are very classical because the interparticle distance is much longer than the Broglie wavelength. Remember that the Broglie wavelength is inversely proportional to the square root of the temperature, and therefore when only when we start to cool down the atoms, the de Broglie wavelength start to grow. And when the de Broglie wavelength becomes comparable with the interparticle distance of the atoms in the gas, is where quantum phenomena start to matter, quantum statistics. And for the case of bosons, for example, they form a Bose-Einstein condensate, where they form a giant matter wave, where all the atoms want to remain in the ground state. This is the phenomena of Bose-Einstein condensation, with macroscopic number of atoms remain in the ground state. This was predicted by Bose for light in 24. Well, photons are bosons. Then by Einstein of atoms in 1925. But it was only in 1995, 17 years after the Einstein prediction, when group in Colorado achieved the production of a BEC, and these scientists won the Nobel Prize in 2001. So we have Early Cornell, Carl Wildman, both from JILA, and Wolfram Ketterle from MIT, and they create a gas of rubidium and sodium, condensates using rubidium here and sodium in MIT. All right, so this is for bosons, but perhaps you are aware that besides bosons, you have also fermions. So bosons exhibit a phase transition as you cool them down. Instead, fermions don't feature a phase transition, but still at similar temperatures at which the bosons condense, the fermions form what is called a quantum degenerated Fermi gas. Remember that fermions, instead of bosons, they experience the Pauli exclusion principle, and therefore you cannot have two fermionic atoms in the same internal level. So instead, for example, if you have two different type of flavors of fermions, that is the ones that I have here in Untitled Trap, they are going at very cold temperatures, they collapse in the minimum energy state that is they can form up to the Fermi energy, and all the states above are actually not populated. Similar scales, density conditions that forming BECs. This was a cooling down of fermions was achieved by Debbie Jean, also here at JILA, using potassium atom. Unfortunately, Debbie passed a few years in 2016, but she was able to start the process of condensing fermionic atoms, opening a very nice window for the exploration of very different systems. And now there are many different isotopes of fermionic atoms that are cooled down in addition to bosonic isotopes. Okay, so then the question is what we can do with this ultra-cold system. And well, the answer is we want to use them to explore the quantum world. And there are very exciting applications that we are thinking to use these atoms for. One is the idea to generate what is called quantum simulators. We want to use them to emulate the behavior of materials, but with better properties. So that's what we call advanced materials. So we can design new type of materials, like, for example, high temperature superconductors that conduct at faster and at highest temperatures, even at room temperature, in a ways that we don't have in nature. We want, of course, might have heard to use these systems for quantum computers and take advantage of these advanced capabilities to surpass the computation capabilities of any classical computer, taking advantage of his quantum advantage. But moreover, we want to use these systems for unravel the mysteries of the quantum world and fundamental physics. For example, connections between general relativity and quantum mechanics. Or we can also use these systems to create the most precise sensors that we can ever prepare using the quantum properties of these systems. So, and the story that I want to tell you today is that these properties that are shared from atomic systems can all be found in a single type of system that are atomic clocks. So atomic clocks are opening us connection to these different possibilities, and I'm going to tell you a little bit of how is that happening. With that, let me start by introducing you, remind you that a clock is a measurement device. It ticks in a repeated manner to measure time. And any clock is made of two basic parts, an oscillator that ticks and a counter that measures the ticking, counts the oscillation. But let's stop and think about the measurement of time itself. We make appointments, we worry about those terrible deadlines, and the question is why we care to measure time so precisely. Well, it has been essential for the mankind to determine what time it is, days, and well, to generate a schedule. So the first clocks were astronomical objects, like what the Egyptians used the sun to record time. Then they were followed by the electromechanical devices, the quartz clock. But the talk clocks that I'm going to tell you today is about atomic clocks that they use atoms and light to measure time. And I'm going to tell you a little bit how is that process happening. All right. The basic idea is that for atomic clocks, what ticks is an electromagnetic wave, so a light source, and the counter are the atoms. So sometimes the ticking of the electromagnetic wave is so fast that even electronics cannot count these oscillations. But on the other hand, atoms can count it. And atoms are unique because atoms share a quantized energy structure that is universal here or in China or everywhere in the world. So we don't have human error in counting these oscillations. So in fact, this idea of the quantization of energy levels in an atom using that for unrivaled definition of the seconds, came along many years ago. And even today, the way that we define the seconds is based on the energy splitting of the cesium atom. Basically, the second is the duration of about 9 billions of periods of oscillations of light in this transition. You can remember that cesium here is an atom in the first column of the periodic table. All right, so the first clock was actually created in 1955 by Essen and Parry, and it was okay. It lost a second every 100 years. That was a good clock, very good clock at the time. But there has been an exponential progress of the improvement of the clock, so from the creation until the 80s. But then the progress stopped, and it was with the invention of laser cooling that I mentioned before for atoms that we can start to reach a next generation of clocks that are called the fountain clocks, that I'm going to tell you a little bit more about that. So why it was this gap between these clocks and these clocks that after laser cooling? The reason is that motion is really bad for clocks. And for that, you can imagine, you are familiar with the Doppler effect. So if you have a source that is moving, then depending if it's going away from you or towards you, you are going to feel different frequency. Well, exactly the same for atoms. If the atoms are moving, then the frequency that we are measuring is going to depend on the velocity, and this is very bad. And that's why only when the atoms we were able to cool down the atoms with the Doppler cooling, that was allowed to start creating the next generation of atomic clock. So here is a movie of the cesium clock, of how it operates. This is just a very simple cartoon. Let's see if I can. No, so 1 second. I have to remove the. Sorry. Why it's not operating? 1 second. Okay. Yes. So this is a very simple video of how it operates the clock. The cesium clock, just to get an idea, and I'm going to connect what we are doing now, because the cesium is not the best clock now that we use. But the basic idea is that we have a chamber where we have the gas of cesium atoms, and then these atoms are going to be cooled down by the laser beams applied in all directions, what I showed you before. And then, we want to lock our frequency of the ticker, that is a microwave, you can see that, with the frequency of the atoms. So the atoms are illuminated by one microwave, they are launched in space, they come back by a second microwave, and the idea is that depending on the frequency of the microwave that we use, we excite less or more atoms. So if the frequency is not on resonance with the atomic transition, we are only going to excite few atoms. when the microwave frequency is on resonance with the atomic transition, we are going to provide the maximum excitation of the atoms, and we are going to use this as the feedback loop to lock our atoms. And when we are farther away from the resonance, again, we are going to excite less atoms. So basically, this is the protocol that we use in order to lock the laser that is quad thick, or the microwave that is quad thick, with the atomic that is quad fields, counts the oscillations. All right. So yes, so we can see that with that we can determine what is the best frequency that what is the frequency of the atomic transition, and we use that to measure seconds. All right, now let me start to go to our next slide. So I was telling you, nevertheless, the precision of the cesium clock is currently not the best in the world, and the simplest way that you can understand that is by looking two rulers, one that has more ticks, one has less ticks, and of course the one that has thinner ticks is the best. So higher ticks, better resolution is the same for clocks. The cesium clock operate with microwaves, so that are very slow. On the contrary, there are clocks that operate with optical transitions that can have 10 to the 4 times faster oscillations than the microwave, and therefore they are better. So, and these are the clocks that are using now here at JILA. In this case, we use a laser to do the pendulum, and we have a similar feedback cycle, but we are going to trap the atoms in what we call optical lattice to actually avoid Doppler motion. So the idea is that the type of atoms that we use is strontium, and this is because it offers a transition that is very long-lived. That if it's very long-lived, it gives us very large spectral resolution. So the lifetime can be longer than 100 seconds. So if you think about this clock and you compare it with a classical pendulum, for that you compute the quality factors, that is the ratio between the frequency of the oscillation, that is an optical transition, compared with the damping rate, that is very slow because it lasts 100 seconds, so it's just millihertz. You have a quality factor that is larger than 10 to the 17, that corresponds to a classical pendulum that when it would start to swing, it would swing for the entire age of the universe. So that's the so good quality factor that we have for the atoms. So now we want to cool the atoms and try to avoid the motion, and for that we trap them in what is called optical lattice or artificial crystals of light. In this case, we use two counterpropagating beams actually to form a standing wave. The atoms have an induced dipole moment that fills this standing wave, and they are trapped at this bottom of the potential. And therefore, if the trap is very tight, like what they do in 1D lattice, they cannot move from one lattice side to the next. So the motion is forbidden along the direction of the propagation of the laser. Moreover, we are guaranteed that the potential that the atoms experience is the same in the ground and excited state, preventing other type of errors. So the spectroscopic protocol that we use is very similar to what the movie that I showed you, but slightly different. What we do is that first we have the atomic transition with the frequency that we want to measure, and our laser that is going to illuminate this transition. The two internal states of the atoms are the ground and the excited state that form a spin system, and this can be represented in a sphere where down it corresponds to the ground state, pointing up correspond to the excited state, and when we have a superposition between the states, it points along for example, if this equal superposition, it points along the x direction. So we use a laser to excite some of the atoms from the ground to excited state with some initial pulse. We let the atoms evolve for some time, and if the laser is not completely locked with the transition frequency of the atoms, then is as in the rotating frame of the laser as if there were an effective magnetic field, and as a spin in a magnetic field is going to precess and perpendicular to the field that is along the x direction and acquire a phase. And we can measure this additional phase by adding a second pulse that transfers the phase into population, and we measure the population of the atoms. So this population measurement is what is called a Ramsey fringe. proposed by Norman Ramsey, who won the Nobel Prize in 1989. And the oscillations are depending on this detuning, and therefore we can use these oscillations to lock our laser with the atomic transition. That's why it's called Ramsey spectroscopy. So this idea works extremely well when we have a single atom. Okay, so the Ramsey fringe has a phase and a contrast, and we can use it to measure, to look my laser. But the idea is that we don't want to use a single atom, but we want to use many atoms to have larger signal to noise. Yes? And that's where June started to think about how he was going to build his clock. He wants more atoms to have more signal to noise, but unfortunately atoms are not transparent. They are particles, so they collide. And when they collide, unfortunately, collisions are bad for the clock, but collisions changes the frequency that the laser measure depending of the density of how many atoms you have. So it's not the same that you would have if the atoms were not colliding. That is what we wanted. So the idea of June said, okay, let's use quantum statistics here to avoid the problem with collisions. His idea was very simple. In quantum mechanics, we have atoms behaving like waves and similar behaviors with the collisions. The collision of the atoms can be modeled in terms of partial waves, and we have a different type of partial waves are allowed depending on the statistics of the atoms. Actually, it happens that fermions that have Pauli exclusion principle, they cannot collide with the lowest partial channel because it's forbidden. Two identical particles cannot be occupy the same internal state, so L equal to 0 collisions cannot happen for fermions because they cannot be in the same state very close. The allowed collisions involve L equal to 1, and this requires energy, so the atoms has to be energetic enough to actually collide and go to another higher partial wave. So that's what Jung wanted. So let's build our system with fermions, because fermions will not collide at low energy, because if they are not energy to jump this barrier to go to P waves, then that will not happen. So unfortunately, to his surprise, the clock was so precise that at this time, when he has a clock of operating with atoms at 1 microkelvin, collisions were the second largest systematic of the clock, were really bad. That means the clock, for Jung was sad. For me, I'm laughing it here because for me it meant that the clock was so precise that was even able to measure these low energy, these suppressed collisions that happens when you have P wave L equal to 1 collisions. So what I did is to develop a model that uses the atoms. Remember, the atoms are trapped in this 1D lattice, where you can see each lattice sides as a pancake. There are many atoms there, but the point is that we are in the quantum world, so the energy of the atoms are quantized because it's kind of an harmonic oscillator. This pancake is kind of an harmonic oscillator. The atoms are if we go to the energy space, the atoms are frozen in this eigenstate of the systems that are quantized. So because they are frozen, you can think of these internal energy states as an effective lattice of the system, because the atoms are going to be pinned in this eigenstate of the trapping potential, and the only thing that can happen is atoms can flip the spin. So, but with this analogy, we develop a simpler model to understand the atoms, and I'm not going to go in detail through it. But what we discovered, or we theoretically found, is that the change in the ticking of the clock because of collisions was a function of the number of excited atoms that were set by the first pulse that we apply in the Ramsey frequency. Remember that we first excite some atoms. So depending on the number of atoms that are excited, then we can have we can change the ticking of the clock. And if we choose a little bit such that there are a little bit more atoms up and down, a little bit more, we can operate in a point when the ticking of the clock is not modified. It's kind of a magic point. And by doing that, we were able to operate a clock that was immune to collisions. And with that, we were able to create a clock that is, at that time, when we were first created, it was 1,000 times better than current cesium standard. June this year reported a factor of even 2 more, a 2 order of magnitude better. But Okay, so in 2015, this clock was 1,000 times better than the current cesium standard. Has a sensitivity of 10 to the minus 18. This number corresponds that is a clock that never gain or lose 1 second in some 15 billion years. That is roughly the age of the universe. That is the kind of clock that we created by understanding the collisions. But the idea is even more appealing, because what it's telling me is that we can use the clocks to understand collisions and therefore to understand many body physics. That is really great. So, any questions so far until here? No? Okay. So let me now tell you in the next second part how we are using the clocks to explore many body physics and to explore all these fascinating properties of the quantum world. So one of the big questions or complications of quantum systems is that quantum superpositions happen in the quantum world, and therefore in order to describe the state of the system, we need many states when we are trying to model it. For example, if we have only 6 particles in 3 sides, and I ask you to count how many ways you can put 6 identical particles in these 3 sides, and you can start counting, you are going to count 84, and this is one example, 2, 2, 2, but you can also have 6, 0, 0, or 6, 0, 0. I mean, if you count how many ways, you are going to tell me there are 84 states that I have to keep track in order to model the system. Just multiply the number of particles by 10 and the number of sides by 10, and you get a number that is larger than the Avogadro number to determine how many are the number of states that you need to access in order to fully model the system. So this number of states cannot be stored in the memory of a classical computer, and therefore it's really challenged, or it's very complicated to model these systems. So quantum systems cannot be modeled with classical computers. So Richard Feynman proposed an idea a few years ago. He was also a Nobel Prize in 1965, and he says, well, maybe instead of doing that, using computers made with classical ingredients, we can build a quantum computer that performs computations using quantum mechanical elements itself. So, and you know that there is a lot of effort trying to create this universal quantum computer. But he also proposed the idea that maybe if we don't want to emulate all different types of quantum problems, but just a specific type, we can use we can create a quantum simulator that is not universal, but we can use one specific system to model another system that has similar behavior, but in one case we can control the system, manipulate it and modify it, and the other, and this is going to be used to model the behavior of other more complex system, like a crystal that has many defects, many complications that we don't understand, but we can use the one that we can control in order to simulate the behavior and extract the most interesting properties. So the idea is that we can use the control of atomic clocks in order to bridge the gap between and understand many body physics. So instead of having a brewery of energy levels, we can use the clock to resolve the different energy levels and try to understand the basic quantum behavior of the system. So a very simple cartoon that I like to explain in very simple terms what the clock is doing for us is, imagine that you are a very bad clock and you can only see your system for short times before decohering. So what did you see? Anyone can say, what did you see? I can try it again. I imagine that you saw kind of a ball. That's what I saw. So now imagine that you are the strontium optical lattice tracker JILA that can probe a quantum system for a very long time. And I'm going to ask you, what did you see? Again, what did you see? Anyone? Did you see an hydrogen atom? There was an edge in the hydrogen. Okay, so that's the idea. So we can resolve something that is very blurry and extract some properties that otherwise we cannot decode. So now, if you want to, in the context of emulating quantum materials, we want, for example, these are very complicated because they have very complicated interplay between spin degrees of freedom, orbital degrees of freedom, and we have also charged electrons. So all these interplays makes these materials very complex. In an strontium atom, we have the two clock states that can be think as an orbital degree of freedom. We have an spin degree of freedom, a nuclear spin degree of freedom, because the atoms, instead of, in addition of the electron, we have the nuclear spin that is large for strontium. And in addition, I'm going to tell you very briefly that even though we are having neutral particles, we can use lasers to make the particles behave as charged particles. So all these properties are in the strontium atoms that we use for the clock. So first, let me tell you an idea very briefly about very briefly about the nuclear spin of strontium atoms. So strontium is in the outer column of the periodic table, so it has 2 electrons, but also have a nuclear spin. And the important part for strontium and why is such good for clock is that the nuclear spin and the electron spin are decoupled. They are not talking to each other because these atoms form a singlet, so it's not talking to the nuclear spins. So we have kind of 2 separate degrees of freedom, the nuclear spins and the 2 clock states to explore in a very kind of separate way. And this separation between the ground, the nuclear spins and the electronic spin of the atoms makes the collisions between the atoms, between strontium atoms, unique, because they have when there is a conservation law, that means that the nuclear spins, because the nuclear spins are independent from the electronic spins, you cannot change the spin of the nuclear spin of the colliding atoms. So you have 1 9/2 and 1 7/2 atoms. They cannot collide and form a minus 7/2 of 9/2. There is a conservation law. If you have 9/2 and 7/2, they have to remain 9/2 and 7/2. And this introduces a unique symmetry in the collisions that is SUN symmetry, that actually is the same symmetry, for example, that you find in gluons or in chromodynamics. So this symmetry happens with n equal to 10. So it's very interesting that in principle we can encode in this type of atoms an SUN symmetry, but actually by choosing the number of flavors. N is when you populate all the different nuclear spins, but if you populate only 2, we can explore SU2 symmetry. Or if you populate only 3 spins, we can explore SU3 symmetry. So we can explore SUN symmetry that is fundamental in many different fields in physics, including high energy. And moreover, for example, when you go to SU10, we can use this N as an expansion parameter. So even if we have a very strongly correlated system, we can use other expansion parameter that is N, not the interactions, to expand. And actually, we have predicted that strontium atoms in a periodic potential can form new state of matter that we form. In particular, we said that they can form a chiral spin liquid that is an analogous of the quantum Hall effect. And just to emphasize the importance of topological phases, the Nobel Prize in 2016 was given to 3 theories recognizing the discovery of topological transitions and phases of matter. So we have predicted that in principle, this putting strontium atoms in a lattice, we can generate a chiral spin liquid, and this can be used as the basis for an error-free quantum computer. So that's one of the applications for the nuclear spin. So some interesting story is that when we wrote the paper on showing that we have SUN symmetry collisions in the clock, then someone from the Big Bang theory, I don't know if you know this series, but sometime contacted us and said that they want to have an episode where Sheldon was going to go to JILA to discover with us the SUN symmetry of strontium. So they said, according to the scientists working in the Big Bang theory, it all began with Sheldon participation in the JILA research team, hoping to confirm via direct observation the spin symmetry theory in quantum physics. Sheldon used to working in the theoretical realm, found his colleagues alienating like Penny. However, under the tutelage of Ana Maria Rey and Junge, Sheldon was learning how best to unify the two fields, resulting in the remarkable new findings. So we never appear in the series at the end. Anything was recorded to JILA, but it was very funny to see that. Okay. So now I am not passing the page. Okay, so maybe briefly in the 10 minutes, in the 5 minutes that I have left, I'm going to tell you a little bit about how we can make neutral atoms act as if they were charged. And one important property that charged particles experience is the phenomenon of spin-orbit coupling. This happens, for example, electrons moving in the solid, where the electron motion and its spin are coupled via relativistic effects. So this spin-orbit coupling, I don't know if you have heard, but is the key for generating spintronic devices. Is the basis behind what is called topological insulators that have very interesting topologically protective characteristics. And moreover, it has been predicted that if you have a material that have a strong spin-orbit coupling and you put it near to a superconductor, because of the proximity effect, we can generate what is called Majorana particles that are the basis also in principle for topologically protected quantum information. And this was one of the directions that Microsoft wanted to explore in his to build a quantum computer. So implementing a spin-orbit coupling in the clock is actually very simple, and I'm going to tell you how. In very simple terms. So the basic idea is that, as I told you, we have the atoms trapped in this 1D optical lattice, as I'm showing here, and we have the clock laser that is illuminating the atoms, but the clock laser interrogates an optical transition. So K, that is the wave vector associated with the laser, with the optical transition, is actually comparable with the lasers that we use with the wavelength, or I mean the K, the wave length, with the wave vector of the laser of the clock is comparable with the wave vector of the lasers that we use to generate the optical lattice that traps the atoms. So basically, if we think these are the lattice sites, and in each lattice site, imagine that we are using a laser to induce a transition from ground to excited. Yes? But the important point is that the phase of the laser changes by AKA from one lattice size to the next. If you have K times A, the lattice spacing in our clock is larger than pi, is significant. So the phase changes significantly of the laser between one lattice site and the next, and the next, and the next, and the next. But now, if we also allow the atoms in these lattices to tunnel from one lattice size to the next, you can see that we can effectively generate what is called a synthetic flux ladder. So basically, here is the spatial direction that atoms can tunnel from one point K to the other. But this vertical direction is the synthetic direction, that is the ground and the excited state. So basically, the basic idea is that if I have one atom at lattice site 1, this atom absorbs a photon and goes from ground to excited, the phase of the lasers that this sees is e to the I5. But then the atom can tunnel from here to here while not accumulating any lattice in any phase. But then it is going to emit a photon from here to here, but the phase is different. If this has phi, this has 0 phase, and then the atom can tunnel again to the other side. And doing this placket, you can see there is a phase phi that is accumulated during the process. And this phi is at the heart of the spin-orbit coupling. It's emulating as kind of particle moving and feeling a very strong magnetic field. So that's the way that we can implement. And somehow you are seeing that by the atom is absorbing a photon, and because the wave vector of the photon is very large, when it do a spin flip, is also changing its momentum. This is the real estate point of view. The other spatial point of view is that the atoms go from down to up, but because the wavelength of the laser that is large, it absorbs a momentum and couples the spins of the atom by flipping with its momentum. So by doing that, we have what we call a spin orbital physics of Flux ladder, and we have explored this in very different settings in the 1D lattice clock, using for a dilute sample or for an interacting sample, showing that we do have and we emulate a spin orbit coupling in these systems. So, but moreover, and this is the last part of the talk, we not necessarily only now have a 1D lattice. Now June has, and remember that I told you that the gas was at 1 microkelvin. Now June has been able to cool down the atoms to quantum degeneracy, to everything quantum, and not only trap them in a 1D lattice, but in a 3D lattice. And in a 3D lattice, all of the degrees of freedom are acting quantum mechanically. He has very low temperature, T over Tf of the order of 0.1. And moreover, if you can think about how we can suppress collisions, if we have one atom per lattice site, and the tunneling from one lattice site to the other is very long, then we don't have any effects from collisions, because one atom doesn't have any collision with itself. So it's just one atom per site, no collisions, and we can suppress even the collisions of the clock. So this, in principle, is the story, but not quite. So this is the ideal scenario from June, that we have one atom per lattice sites. And remember, there are fermions. So if there are fermions, you cannot tunnel from one lattice site to the other, because you cannot have two identical fermions in the same lattice site. It's forbidden. So this system, in principle, is the ideal clock, because you have as many atoms as you want, but you don't have any collisions, you don't have any motion, nothing. Everything is frozen perfect. But that's not the reality, because the reality is that when you interrogate the atoms in the clock, with the clock laser, remember we have this spin orbit coupling, this phase of the laser changes from one lattice site to the next, making the atoms distinguishable, because now it's rotating, the atoms feel a different phase, so they're not the same. And if they're not the same, because of what we call the spin orbit coupling, then the atoms can tunnel from one lattice site to the other, because I can have two different atoms in the same lattice site. The Pauli exclusion principle allow me. And then I have collisions, and I have also nasty things. So that in principle could be not ideal. But now the idea is that even though we have something not ideal, we have also an element that we can control, use for control. The idea is that imagine that we use a lattice that is very deep along the z direction, so the atoms cannot tunnel along the z direction, but they can tunnel along this direction, the xy plane. But now the spin orbit phase that the atoms feel are only the projection of the laser, the k vector, along the direction that they can move. So there is a control now, because the projection of this laser along the xy plane can be changed by changing the orientation of the laser. So if we have the laser completely parallel, there is no spin orbit coupling, and in principle we have this system. And if we make the laser a little bit with some tilt for the parameters that we can have a spin orbit coupling angle that is pi. So why am I using that? Because we have shown that this spin orbit coupling with interactions and with tunneling can allow us to generate very different type of gates that could be also serve the basis for the next generation of quantum computers. So the interplay between spin orbit coupling and interactions, we have some recent papers that we can use not only for entangle the atoms in the clock and make them better sensors, that is something what is called spin squeeze states. We can use this to make states, atoms that have less noise that if a classical atom could have, a non-interacting atom have. We can also use this spin orbit coupling to create some type of very strongly interacting state that is called cluster state. These cluster states are the basis of some type of quantum information protocol that is called one-way quantum computer, that when you create this cluster state, and then in order to do gates, you just measure. So we have the capability to create, in principle, cluster states in the clock. Or we have also shown that using spin orbit coupling and interactions, we can create cat states that are also very important states for error correction and for other type of resources for quantum computing. So with that, I hope I can convince you that there is it's just the beginning. There is bright vista ahead. We have used clocks to be the best timekeepers ever, but now we can make it even better by using the properties of quantum mechanics. That's something that we are working on. In principle, we can use these clocks to build the basis of next quantum computers, still to be done, but with great potential. And because these atoms are so precise, we didn't have time to talk about it, but we can also use these atoms to sense, for example, gravitational redshifts, or to measure the curvature of our space-time, and with that trying to merge gravity with quantum physics, and hopefully unravel many of the open questions that we have in coupling the microscopic to the macroscopic world. And with that, I'm open to questions, and thank you for your attention.
Oh, thank you so much, Professor. And please, if you have any question, then please ask. I think I can start the questioning because I have a question about the cat state that you mentioned at the last part of the lecture.
Yes, okay.
Is it related to the Schrodinger's cat and then like keeping the coherence somehow? Would you explain a little bit about that?
Yes. Yes. The basic idea of how you create the cat is that we can have atoms. Let me see if I can write. Let me stop. 1 second. Let me try to stop here, and then let me try to share my screen. 1 second. If I think I should be able to share my screen. I still sharing. Let me share very quickly, and I can explain you what is the idea. We have the atoms in an optical lattice, but actually there is also an harmonic trap. So the lattice is more like this. Okay. Like this is how the potential. And then I have two internal levels of the atoms. This is up and down, up and down, up and down. Something like that. So this is the two possible energy states of the atoms. So with a spin orbit coupling, you have to believe me that this is possible. What we can make is that this atom, I imagine that I prepare some atoms in these states, here. Sorry, I'm preparing these atoms here. I prepare some atoms in the ground state. I mean, this side is occupied. So, and what happens is that with the spin orbit coupling, I can set a system where I first allow this atom to tunnel here, from here to here. So this atom tunnel from here to here. So there is a hole here. Now what happens is that this atom, so I imagine that I create a superposition when I have my first atom up and then other atoms down, something like that, and a superposition of this state with all atoms down, all are down. Yes, something like that. This is my initial state. This is not entangled at all because it's just this is a superposition of the first atom is a superposition of up and down, and the rest is down. So I can, with the spin orbit coupling, I can precise a process that only when I have a state, when only I have up-down atom, so when I only have nearest neighbors, this atom can tunnel and flip the spin. So after this process, this atom can tunnel here and go. I'm going to create a superposition here initially with two atoms. These are two atoms here. Yes. So how only when these are two atoms, and this is down, I can tunnel and flip my spin. So after first I'm going to tunnel and flip my spin. So, but if I have something like this, I never tunnel. So what happens is that this atom can propagate from these atoms can start, this double occupied side can propagate from here to here to here, but leaving a chain of spin up atoms. So the first process, for example, this flip to one up, and then I have my pair here. Yes, and then the rest down. Then this atom flips and then I can create a state that is up, up, and then my double occupy atom here. And then after many processes that are done with via the laser, I can create a state where all my atoms in this state have flipped from down to up. I have my double occupy side at the end that it doesn't matter. And I have the other state that is all down. So this is a cut state when this is up, plus all is done down. And I mean, at the end there is a defect, but doesn't matter. So that's a process that we can use spin orbit coupling interactions at the laser to start with something that is trivial and then create a superposition of all up and all down. Plus, I don't know if this answered your question. I mean, I know that is, I mean, I'm giving you not all the details, but this is the idea.
So the reason why it's called the cat state is because it preserves some quantum information, even though it becomes a macro state.
It's a cat state because the state is all up plus all down.
Oh, I see. Okay.
So this is a cat state because it's like the cat is dead or alive. So this state is a macroscopic system, and this state is, for example, the cat is dead, and this is the case when my cat is alive.
I see.
And that's what we can, in principle, do in the clock, and that's in principle something that could be used, for example, for error correction, or can be used for a metrology too. So there are different things that can be useful for.
Oh, I see. Thank you so much, Professor.
Great.
Yeah. Any other question?
Hi. So that was actually kind of interesting, the last bit. But I'm a little bit confused why exactly it leaves this trail of flipped upspins. If you
Okay.
have mind explaining exactly how?
Yeah. Okay. Yes. So let me share my screen again. 1 second. Share my screen. With the spin. Okay. So the point is that okay. Let me explain a little bit more for 2Ls. With the spin orbit coupling, we can try to do something that we can open an energy penalty. This is an energy splitting between the up and down that we call disproportional to the Rabi drive. So imagine that I have an atom here. Yes. So I mean, the spin orbit coupling, for example, the phase that we have is pi. The phase that we have is pi. So that means that along one well, this is pointed along x, and the eigenstates here are pointing along minus x, and along this well is the opposite direction. Yes. So the important point is that imagine that I have all my atoms initially in this upper level. Yes. The point is that only the atom, only when I am going to change my state, I mean, this atom, whenever this atom can tunnel, only when it goes from this higher energy state to the low energy state, because this, when I have already one atom here, yes, and then when this goes here, it reduces some energy omega, because this is plus, this has omega, but this has less omega. But when you have two atoms, we gain interaction energy U. So we decrease energy omega. We decrease energy omega and create interaction energy U. So in this process, the atom tunnel and its resonance, if U is very close to omega, so this can tunnel. This when the atom is in the higher energy state, can go to the lower energy state, because there is interactions, and this can happen. On the other hand, if you can see, if I have an atom in the lower energy state, that cannot happen. Yes, if I have an atom here, for example, and I have an atom here, now instead of being here, is in the lower energy state. When this atom here, it has to increase energy plus omega, and then increase interaction energy. If this atom goes from here to here, it gains omega and it gains interaction energy. So this process is forbidden. So only when you only one type, when you are up, you can tunnel. When you are down, you cannot tunnel. So that's why the state that we prepare, that's the idea. So we start with all atoms. And in one case, we start with all atoms, and we can create this double occupied site. And then in one case, this atom can tunnel, and when it tunnels, it flips the spin. So this atom, when it tunnels, is go from up to down. And in the other case, when the atoms are all down, then nothing can happen because is this process. So nothing can happen and the atoms cannot flip. So when the atom tunnel is going to, as the atom tunnel from here to here, is going to, so when the process is that an atom is in up, when it tunnels, it can become up because there is another atom here. It can, I mean, all the atoms are here in the ground state. All the atoms can tunnel in the ground state, and this atom in this case can tunnel here. This atom can tunnel here, and when he tunnels, it's going to, depends on the basis, but when one atom move, it can tunnel here and flip the spin because it goes from up to down, and then we can create a change. Whereas in this case, is this case that the atoms cannot tunnel, and then everything gets in the. So these atoms, in this case, there is no way. So only when there is a doublon here that we've initially prepared, this atom can tunnel because the energy is U minus omega. These atoms that are here, that there is no a doublon, they cannot tunnel because to cost too much energy to move. Yes, so the down atoms get all down, whereas this atom, they start to tunnel, and when tunnel, it flips the spin, so it leaves a chain of atoms in behind as it tunnels. It goes from up to down, but in the process, this process is going to be, you have an atom here is up, this atom is down, and the process that is allowed is that this moves here. Whenever this happens here, this atom, for example, I'm going to put a doublon here. This atom here is a doublon. This is down. So this atom is going to be allowed to tunnel here, but leaving this spin flip. And when this happens, then you can create these are too much details, but the basic idea, I will have to go. There's a lot of change in bases that happens, but the basic idea is that with the spin orbit coupling, we can allow only one species to tunnel after some changes in bases, and then you can create a string of up, and the atoms can start moving and creating. The downs cannot do anything, but the ups, where there is a double occupy, can tunnel and let a string of up atoms in behind. So that's the process. I can, if you are interested, I can show you more detail. Maybe we can read this reference here, but I don't have. This idea, this talk is exactly for that. For tease you to try to tell you that we can use spin orbit coupling and interactions and tunneling in order to generate very interesting states.
Yeah. No, definitely. Okay. I think this got us pretty interested. We'll check it out.
Okay, sounds great.
So, which reference is this? Do you mind?
Yes, I can share with you. Is this paper? Can you see my screen? Can you? Hello?
Hi, sorry. I think our internet cut out. Are we back?
Yeah, is PRA is this paper?
Okay. Awesome. Awesome. Thank you very much.
Yeah, thank you. Okay, so it looks like we are nearing the end of our time. And Professor Rey, as is tradition, we like to ask the speaker for a quick word of advice for young physicists looking to start their journey through physics.
Yes, so I think my advice is to work hard and work very hard and try to, and because of that, choose a topic or a field that you like very much, because that will allow you to work as hard as you can.
Oh, thank you so much, Professor. And I wanted to thank you again, Professor Rey, for an excellent conversation today. It was really a pleasure to hear about your career and your current research interests. Although our Quantum Summer series and with Professor Rey's talk today, we will follow up with you on next Chilloquium talks in coming weeks. I hope to see you all next time. And again, thank you so much, Professor Rey.
Okay, thank you. Bye-bye. Bye-bye.
Thank you.